Alright, so here we are for part 2 of the lecture for students watching this semester. This is again on August 1st, 2016, and this is lesson number 26 in our video series. Alright, so let us begin. Alright, we are going to be working through section 6.4 in the Hibbler text, and we are going to be learning about a few things. So first, let me list the learning objectives for this session. We wish to first explain how stress and strain vary from the neutral axis, relate the stress to the internal bending moment and geometry of the cross-section, use the flexural equation and describe the significance of the area moment of inertia, and finally calculate the area moment of inertia, or I, for a beam cross-section. Okay, so now let us discuss beams. Fundamentally, your moment of inertia is what you use to transform the shear and moment, well actually just the moment. Okay, let me back up. In the previous lessons, we have learned how to calculate shear and moment from loads along a beam. Now, what we wish to do is we wish to actually transform those into stresses. Ultimately, we use stresses when we design objects. We're not really concerned how high a moment is in a beam or in a section. We're concerned whether the moment that is being applied is going to exceed some sort of stress in the material. And moment of inertia is an area is what we use for relating shear to stress, and moment of inertia is what we use to relate moment to stress. So hopefully that was clear as mud, and let's move on. Okay, so we have seen beams before, but I don't know if I've ever actually rigorously defined what a beam is. So what does a beam mean? Well, fundamentally, a beam is a structure. A beam is a structure with load perpendicular to longitudinal axis. You have a load perpendicular to the longitudinal axis. That is what makes a beam, just like a column is one that has loads along the axis. Okay, and we classify these according to their end conditions. Classified by end conditions. Classified by end conditions. So first I'm going to have a simple beam, or a simply supported beam. Oh, that looks awful. Let me fix that. Oh, let me fix that here. So if I have a beam with a pin on one end and a roller on another, with some arbitrary, so let me just draw the three cases first, and then I'll describe these here. And then I'll draw some loads on them. Although the loading is completely arbitrary, they're defined by their support conditions, not their loading. So say I had something like this, etc. A pin here, roller here, and a roller here. Let's see. So let me just put some loads on these things. So maybe I'd have a load like that, maybe a load like that, maybe a load like that. And I'm going to call these are called, well, as you might imagine, this is a simple beam or a simply supported beam. This is a cantilevered beam. And this is a continuous beam. Also a statically indeterminate beam. Continuous beams continue through more than one span. So they they have more than 3 reactions, and they end up being statically indeterminate. So one span, and in terms of what a span is, formally a span is I would define a span as the distance along a beam between 2 points of vertical support. and this continuous beams are statically indeterminate. Now, each of these have certain advantages and disadvantages, at least between, say, if you're talking something like highway bridges, a simply supported beam has the advantage that it's easier to construct. You can use a lot of times you can get away with using entirely precast or pre-stressed sections, so it's very efficient to build. This one usually takes a bit more effort to build and construct, and does take a bit more effort to design, but the nice thing about it is it is actually a more efficient structure, which you may learn in later courses. Okay, so let me define pure bending. Let me define an idealized state of pure bending. Pure bending. Here. Alright, so we start with an initial delta x, or we start with a purely straight beam. We start with an initially straight beam, despite my drawing to the contrary. So this should have two perfectly horizontal lines, but I can't draw, so there we have it. So we're going to have some length along this beam, delta x. And this beam is initially straight. The beam is initially straight here. And it has a constant cross-section. It's made of nice friendly materials, etc., etc. Constant cross-section. Constant cross-section, and we are going to work under the assumption that plane sections remain plane. Plane sections remain plane. Remain plane. So in other words, if I were to cut a horizontal slice along this beam, as I bend this, the order of the horizontal slices doesn't change. Plane sections will remain plane and parallel to each other. Okay, and especially for small deformations, this is a perfectly satisfactory assumption. So let us consider this. I'm now bending this beam, the same beam, under a pure bending moment applied on either end. So we would not have any other loads, not have axial or transverse loading on here. We would simply have our moment M and M here, like so. Now, let's see. How to define this? Okay. So now let me show that delta x is going to be curved. We're going to have a curved delta x now. Here. Delta x is the change of length along the arc now. So it's a curved length. And finally, with the plane sections remain plane, let me exaggerate the cross-section, a piece of the cross-section. Not the cross-section, just a piece, just to show a exaggerated or a greater, something you can see the curvature a little better. I'm trying to think of proper terms, but it's escaping me now. The piece that we can clearly see the section. Okay. So let us say I have, I'm going to take two cuts here. Let's see, BB and AA. Okay, just a moment here. Okay. Now, so I'm going to have a few delta x's here. Now let's look at this. So really what I'm doing here is just deriving a few things. First I'm going to have a cut AA here, AA, and then somewhere down the line I'm going to have cut BB. Oh, that's A, not B. AA and BB, and AA is parallel to BB. Okay? And I have a line going down the middle of the section known as, and so I'm going to have an NS, let's say I'm going to have a delta X here and a delta X here. And I shouldn't say actually that delta X is going to be, that this line is in the middle. It doesn't necessarily need to be in the middle. So this is called the neutral surface, NS. NS is the neutral surface. NS is our neutral surface. And notice what this means. So this is the neutral surface. And what we are saying about the neutral surface is that if you look here, two parallel lines are if we have a parallel line here and a parallel line here, the point where the second line intersects the end of our section, that is going to be the end of our piece of the beam. That would be the neutral surface. In other words, this is the point that is not undergoing any deformation. So here I'm going to have a well, first of all, let me show you this. I'm going to measure C from the neutral surface. C is the distance from the neutral surface. And I'm going to label DD as the neutral surface. DD. Confused yet? Okay. And then I'm going to have, actually, sorry, how do I want to explain this? Yes, okay. Let me just define a few terms here, and then I'll also, let me just finish my drawing, and then I'll, in the next slide, I'll define some things a bit more rigorously. Really, C, I should put it more, you know what, I'm going to put C as more of a dimension. I think that might help a little bit more. C is really a dimension here, and this is going to be delta C, lowercase delta C. And then Y, I'm going to use an arrow to indicate that it's more of a measurement, something that you can have different values of for a single system. That's Y. Okay. So compare these notes to the previous diagram. Bending flexure. Bending flexure. You know, I wonder if I can fit them. You know what? I think I can fit this stuff on the previous slide. I think that'll make a little bit prettier diagram, or notes anyway. Okay, so let me try to cram this on here. I think it'll work. So bending flexure. Bending flexure. Well, first of all, let me define, this is just where I'm going to define a few things. DD is the neutral surface. Where change of a length is equal to 0. And S, delta equals 0. So you notice, here you can see what's happening here is this thing is in positive bending. Delta X is a fixed length. We're talking about a little minuscule length of the beam. But notice, in this portion of the beam above the neutral axis, and we're assuming positive bending here, the beam is getting shorter than delta S. So delta S up here would be all the way out here, so it's losing length. In other words, it's in compression at the top of the beam. Here, our beam is gaining length. Below NS, our beam is gaining length. It is longer than delta S. So we have, this thing is going to be in tension. So DD is the neutral surface, NS, where the change in length is 0. C is the distance. This is important, so do remember this. C, it's very important. C is the distance from neutral surface, from NS, to the furthest fiber. So it is the distance from the neutral surface to the furthest fiber. And we're going to have the following relationship here. Delta is going to be strain times L naught, which is simply going to be equal strain times delta X. Delta X in this case isn't a change in X length, it's just like delta X is just a little piece of the beam that we're analyzing. If that wasn't clear. Now, we realize that that this is going to be a linear relationship because this is elastic. So let's see. I'm going to have the following relationship is going to occur. Delta at C, the change in length at C, delta at C over C is going to be equal to delta at Y of Y. Or we could say, from this, we could say that strain as a function of Y is equal to Y times strain at C, the outer fiber, over C. In other words, strain is linearly distributed. So therefore, strain is linearly distributed, just like in torsion, pure torsion. Strain is linearly, well, as long as we're not assuming exceeding the elastic stress, but that's something different. Actually, sorry. In torsion, the strain is always linearly distributed, just like in bending here. But the stress will be linear as long as it doesn't exceed the elastic stress. But strain is always going to be linear. Okay, strain is linearly distributed. Strain is linearly distributed. And I can have the side view. If I can look at the side view here. So in other words, if I were to plot the strain here, side view, let me plot the strain in a cross-section of a beam. Like this, here. And it's going to be like this. So we're going to have negative strain here. We're going to be, the top of the beam is going to be in compression, and the bottom of the beam is going to be in tension. Or, again, all of this is assuming positive bending. So like this, and like this. And we have a nice linear relationship between with our strain. So let me erase that a little bit here. Clean that up. And we have it like this. So we have a positive strain below and a negative strain above. Tension below the neutral surface and compression above. Okay. Now, so we have our relationship for strain. Now the question is, can we use that to get a relationship for stress? So I am going to assume elastic, like we usually do. So I'm going to assume elastic. assume elastic. So what will that give me? If I assume this is elastic, and later on, in later sessions, we will learn about plastic bending and partially plastic and all that fun stuff. But for now, that's going to be exam 3 material, which actually all this is exam 3 material, but we'll be seeing that later. So what do I mean by elastic? Well, I'm going to say that strain is equal to stress over the modulus of elasticity. And also, while I'm at it, I'll just go ahead and assume it's homogeneous, nice, friendly materials. Homogeneous, isotropic, all that good stuff. So, what I can then say is, what will that give me? This will give me that I'm going to have the following. The stress at C, the stress of the outermost fiber, over the length of the distance, basically the distance to the outermost fiber, is equal to the stress at any y value, any distance from the neutral surface, over the distance to any the distance of any point to the neutral surface. So therefore, stress is linearly distributed. Stress is linearly distributed. Again, only for elastic. We have to be under our elastic limit. If we exceed that, our assumption is no longer valid and we're going to have a problem. Only for elastic. Okay? So, in other words, I could draw the, if I were to draw the, let me draw a little bit graphical 3D one. I'm going to try to make another lovely 3D diagram like I always do. So let me do this and see if I can, let me try this and see if I can do this without totally screwing it up. Like here. So let's say we had it as a simple rectangular beam. You don't get much simpler than that. Well, I suppose you could have a square, but okay. Then I'm going to have this here, and another like this, and the neutral surface is going to be just at some level. I'm going to draw it as it's like, I'm going to draw it as though it's in the middle, but it doesn't have to be in the middle. It will generally only occur in the middle for, say, a vertically symmetric beam. If your beam is vertically symmetric, then it will be in the middle, like say a nice W section or a rectangular beam or even a circular beam. I don't know why you would have a circular beam, but I suppose you could. That wouldn't be fun to find the moment of inertia of. Well, I guess if you just use a formula, that wouldn't be that bad. Anyway, now if I gave you a hyperbolic beam and asked you to find the moment of inertia on that, we'd have all sorts of fun. Okay. So, I'm going to have this is the neutral surface. When we're talking about a surface, it's called the neutral surface. When we're talking about a single point in a 2D diagram, I would call it the neutral axis of a beam. Now, the stress in this beam. So I'm going to draw the stress, and it is going to be, well, up here, it's going to be going to the, left. In other words, it'll be negative. So I'm going to draw it like that. So that'll be kind of like this. Sort of like this. I know it looks like a monkey drew this, but oh well. So let me connect that. Nice and linear. And connect that. Again, perfectly linear diagram. Like, there you go. And then I can have a compression in the opposite direction. Or sorry, tension in the opposite direction. So this is going to be in compression, and down here is going to be in tension. Again, and we are again assuming positive bending. If you have negative bending, you would reverse all these arrows. And we'd be like this, and then like this. So we have these two stress distributions, and what's going to happen is, if this is a stress distribution, if you think of this like a distributed load you'd have across an area, like a pounds per foot or a PSI or something like that, what this is going to do, the moment about the neutral axis, all of this is going to come together to create the M. If I took the moment of all of this about the neutral axis, I would get the overall moment in the section. So in other words, the stress distribution is going to come together to create or to equal the moment that we have been getting from shear and bending moment diagrams. Okay, so let's see how we can do that. All right, let us get internal force. In order to get a moment, I would first like to get a force. It's usually easier to get a moment if you have a force already. At least I think so. So let us consider internal force. Again, we're going to keep in mind that this is pure bending. So we're looking at an idealized state of pure bending. Now, let us keep going. I'm going to draw the same kind of thing I did before. Yeah, it'll be fine. I was thinking about putting this drawing on the other one, but that's okay. On the other slide, but that's okay. Oh, that's bad. So let me draw the same beam cut. I don't like how that looks. The same cut beam. And it's going to come down like this. I'll move over like this. And then it's going to come down. And like this. And the neutral surface, I'll just go ahead and draw it in the middle. But it doesn't have to be again. The neutral surface is indeed a surface. So neutral surface here, NS. However, right along the cut, if we were looking at the 2D case, this would be the neutral axis, NA. And again, Y is the distance from the neutral axis. So Y would be positive here or negative here. Now, let's see. So, let us look at the elements of force here. Now, I am going to have some force. So I'm going to consider two little elements of force, one compression and one tension. So let us say I have little dAs of force. Little dAs of force. And each of these dAs are going to be a certain distance y from the neutral axis. So these dAs are under a certain stress. And from these I can get a dN. dN is a tiny element of force, the differential element of force, the differential element of normal force specifically. So dN is going to be the stress as a function of y, dA, here, this one in compression, and this one down here, same magnitude but in tension. dN is equal to sigma as a function of y, dA, like so. And all of these together, all of these differential elements together, must join up and form the overall moment at the cut, MR. And then N is going to be the integral of sigma. No, I don't like this color. This is a weird color. I want it black. Oh, I shouldn't say that's a weird color. It's more maroon. I definitely wouldn't call that a weird color. Just I only use that for emphasis. So we're talking about the actual overall axial force in a piece. I could say N is equal to the okay, for a state of pure bending, let's look at this, is going to be equal to sigma of y dA. However, this all has to be equal to 0. So all of the normal force, the compressive normal force must balance the tensile normal force. Okay? So again, I could state that the sum of forces in tension must be equal to the sum of forces in compression. They have to balance each other out. Okay? Then I could say, let's see, we recognize that volumes of stress will equal force. So the MR, the moment, then, is equal to the integral of sigma of y dA times y. Or you can think of this as this is our force here, our N, and this is our distance, our moment arm between them. Or just the distance to the, if we're taking moments about the neutral axis, just that. D is just the distance to the point we're summing moments about. And so we can think of this as volume of stress equals force. The volume of stress equals force. Volume of stress equals force. Okay, so now let us find flexural stress. Flexural stress. So MR is going to be equal to the integral of y, sigma of y, the y times the sigma of y dA. But we know that is equal to, but we can pull out a few constants. We can say this is equal to the sigma at C over C times the integral of y squared dA. If we just apply this relationship here. Y squared dA. However, I've taken statics. Oh, hell, I've taught statics. I know what this formula is. I've seen this before. You've taken statics. You should all know what this formula is. The integral of y squared dA, this is the moment of inertia. I, your area moment of inertia. So now we're on to something. So MR then, just the moment at the point, or moment at the cut, is going to be equal to sigma at C, oh, I don't like that, wrong color, is going to be equal to the sigma at C, in other words, the stress at the outermost fiber, over C, I, or if we have a system with compression, or if I actually want to take this, if I want to take into account some, if I want to take into account sign conventions, I might say this is equal to negative sigma of y over y times I. So again, sign convention, this is sort of explaining where the negative is coming from. If our x is a long beam, y is vertical above the beam and z is transverse to the beam, we are taking a moment positive about this axis here. And you just need a moment, you just need a negative sign in order to balance that. But generally that's not as important as you might think. So sigma as a function of y is going to be, sigma as a function of y is negative mr y over I. All right. Now so that's one way you could think of it. The FE packet, the packet you get on the FE exam, uses a slightly different notation. That's fine. FE packet uses a slightly different notation here. And that's to say, like this, that if you have a linear stress distribution, with your neutral axis in the middle, this is also very common. This is your neutral axis in the middle. Then I can have my linear stress. I want that to be red. I like doing stresses and forces in red. Oh, that looks god-awful. Ugh. Let's do this. So they're drawing it the opposite direction. But anyway. Sometimes you also see it just shifted around. Where sigma x is negative my over I, because they're measuring y like this in a consistent way. Y and c is the distance to the outermost fiber. And then, so c again is c furthest distance from neutral, furthest distance positive or negative from the neutral axis. From the neutral axis here. And then sigma x max is equal to simply plus or minus mc over I, assuming a vertically symmetric cross-section. Okay. So let's see. What if we wanted to find actually be able to locate the neutral axis? So locate neutral axis. This is going to be somewhat of a review from statics, a review from the unit in statics where we learned centroids. So locate neutral axis. Well, so first of all, let's review centroids. 1. Centroid review. So you start by finding the centroid. You start by finding the centroid of a cross-section. And for a single object, an object or a section composed of a single shape, y bar is simply the integral of y dA over the area, integral of dA. But what if you have a composite shape? So I have something like, maybe I have a piece 1 and a piece 2. Say I had a T-beam here. I'm not going to do this with numbers, but I'm just going to illustrate the idea. So say I had piece 1 and piece 2. Each of these is going to have a certain centroid. Each piece is going to have a centroid. And the vertical component of each piece's centroid, we say y1, or the vertical coordinate of each piece's centroid would be something like y1 and y2. Now, if we don't have to use an integral, or you can find, if you're just using area formulas or things, something like that, y bar of the entire thing, we can get rid of the integral signs and say the summation of y dA over summation of a, which is just going to be y1 a1 plus y2 a2 over a1 plus a2 plus a2. That's y bar. Okay? And let's see. How else can we express this? Okay. Let's see. And the FE equation packet expresses this as, another way to think of this is centroid of area is where YAC equals MAX over A, or where XAC equals MAY over A, where MAX is the area moment of inertia, the sigma of YN AC, and MAY is equal to the summation of XN AN. Okay? So once we have the centroid, the next step is to let the neutral axis be the reference line. The centroid is the reference line. So what happens if we do that? Let's investigate that. 2, let the neutral axis be the reference line. So we can say y bar again equals the integral of y dA over the integral of, oh, I don't like that. Let me break this up into 2 clear integrals. The integral of y dA over the integral of dA. Therefore, y bar integral dA is equal to the integral of y dA. Makes sense? But n, as we saw earlier, is equal to the integral of sigma of y dA is equal to sigma at the outer fiber, sigma c over c integral of y dA, and the overall force has to come to 0. So the sigma c over c y bar dA equals 0. If our, again, when we're letting the neutral axis be the reference line, the y bar would have to equal 0. We're letting the centroid equal our, if we let the centroid equal our reference line for stresses. So the real takeaway of all this, if you don't want to get lost in the integrals, is therefore the neutral axis is at the centroid for elastic bending. For elastic. Only for elastic. Don't try to use this on plastic bending. The neutral axis, so that's the real important takeaway here. This is sort of a rough proof of that. You can read more about it in the book. That's the general idea. The neutral axis is the centroid is exactly at the centroid for cases where we have elastic bending. Okay. Now, let's move along. So, area moment of inertia. Area moment of inertia. I. What is this? It is the measure of cross-section, a measure of the cross-section's ability to resist bending. For simple shapes, you can use a table. For standardized steel shapes, you can actually look up something in a table of shapes. Simple shapes use tables. Compound shapes we use this. We find the I of each piece in a compound shape about the neutral axis, which is just equal to the I of the piece about its own centroid plus AD squared. This is the parallel axis theorem, where D is the distance between the piece's centroid and the overall centroid of the entire shape. And then I is simply the summation of all the individual pieces' moment of inertia about the overall centroid. I know that was a bit confusing, but hopefully that is clear. Hopefully you've remembered enough about that from statics. But I don't want to work through an example of parallel axis theorem. I do have an example that I will show you that I'll just throw up on the website or on Blackboard for reference. But again, that's statics. I think you all know how to do that by now, at least hopefully. But if not, please review. You'll need to know how to do that on the exam. Alright, that should do it for today. If you have any questions, feel free to email me. Again, sorry about the late lecture times and video postings. Just had some technical difficulties today that I had to resolve. I will be posting a lesson at a regular time tomorrow, bright and early at 11 a.m. Well, starting at 9, finishing towards 11. But that'll do it. So if you have any questions, feel free to email me. And as always, thank you.